how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to be solving some problems with torque. Now keep in mind, this is one of the more difficult problems in terms of math. As you can see, there's a lot of math on the board. So hopefully you can follow me with this. Remember, watch these videos multiple times. All right, if you're not too sure what's going on, you can also in the comments, I haven't mentioned this before, but in the comments of these videos, you can ask questions. I'll answer them. If you have any questions about what's going on in a particular video, just ask the question in the video or in the comment section, and I will answer back to you anything that you need. So let's get started here. So we got two ladder problems, and then one where a dude's just kind of like standing on a board that's being held up by two ropes. So here we have a ladder with a length and a mass. If mu is 60, which is the static mu, right? This thing isn't moving. What is the angle between the wall and the ladder? Assume no friction between wall and ladder, only friction from ground and ladder. So, and maybe to make this more clear, because I also have my axis of rotation there, let's get started here. So the first thing you want to do, I know I have a lot of things going on here, but the first thing you want to do is you want to draw your free body diagram, okay, which is exactly what I have done here. Sorry about this. Okay, which is exactly what I've done here. I have my normal force from the wall, right? The ladder's leaning against the wall, so there's going to be a normal force from that. The weight of the ladder is pointing down, and we typically, if we're not too sure where it is, we just draw it in the center. We talk about the objects. All objects have a center of mass, and so typically that's where the weight is distributed. So that's typically where we draw it. So the mg of the ladder is right in the center of the ladder. And then on the ground, the ladder is touching the ground. We have the normal force from the floor. I know that looks like friction, but it's floor. And then the friction force that's not letting because the ladder wants to slide out, right? But there's friction pushing against the ladder so it doesn't, again, slide out from the ground. So that's what we're we're looking for angle here. That one's looking for friction. So, all right. So that's our free body diagram. Normal force from the wall, mg, normal force from the floor, and friction. Okay, and you can totally, if you want to, I know this is weird, I drew it here, but if you want to, you could draw friction right here as well. Whatever makes sense to you, I just drew it there. But if you want to draw it there, that's fine too. So either place is important. Don't draw two. I'm not trying to draw two here, but that might be more intuitive to you, and I drew it over here a little bit different so that maybe you can just see both ways. Okay, so got our forces. That's all good and fine, but we're looking for the angle. They're asking us what is the angle between the wall and the ladder. This is what they're asking us for, right? And we were given the length of the ladder, right, the mass of the ladder, and the static coefficient of friction down here. So since they're asking us for the angle, we know, because we might be saying, okay, well, we can solve this stuff with Newton laws, right? You see them down here. There's Newton laws on the board, so they must be for something. But we know that in terms of the way this is, right, if we look at things in terms of our y, right, and our x components here, there's no angles between any of the forces. The forces don't have any angles, right? They all sit on the plane of the, right, either directly in the x or directly in the y, right? So we say, well, I can't do that. There may be a tool that I can use, right? So again, I should have stated this at the beginning, but we know torque. We could solve for torque and see how efficient a force is going to be at spinning something. Or we can use torque as a tool to help us just find forces, because we know torque is a force, so we know applied force is in the torque equation. And that's what these two problems are doing. Actually, all three is using torque more of a tool rather than looking directly for net torque or something like that. Keep that in mind. So again, these are how to use torque as a tool to solve problems. All right, so since we need the angle, we know torque, right? We've been studying torque for a while. We know torque has the angle in it, right? And so you may say, oh, well, I may want to use torque to go about solving this. That's pretty much how you get there. Again, you can imagine, okay, well, if this wall wasn't there, this ladder is going to rotate, right? It's going to fall this way, so it'll kind of rotate around there. So you could think, okay, well, this thing could potentially spin, right? So because of that, torque is an option, okay? You might say to yourself, well, I know torque has an angle in it, but you're not too sure if you can use torque. If there's a chance, or if you could look at something and say, okay, well, if that force wasn't there, this thing would spin, even if the thing never leaves and some object's in equilibrium, and in terms of the way it's built, that force never goes away. If you just imagine, you say, well, if I imagine that force going away, this thing would spin around a certain point, and I can look at torque in terms of that way. So we want to look at this in terms of how this thing would spin, right? If we put an axis of rotation there, and I guess assuming that the wall fell away and the ladder fell, we would get a twist. But right now we're just in equilibrium, so we can use torque in terms of Newton's first law. And we know that when there's angles, right, we know there's an angle here, but we know that when there's angles in terms of our lever arms, right, or the force isn't perpendicular to the surface, so this is the surface of the ladder, and we can see that in terms of these forces, none of them are at an, right, this would be perpendicular. If there was a force in this direction, that would be perpendicular to the surface, and then we would use FR, right? We use FR for perpendicular, right here, they're perpendicular like in this situation. But they're not, so we know that since the forces are perpendicular to the surface, the torque equation we use is torque equals force times the lever arm, which means we got to find the lever arm. So instead of making a messy picture, that's what I did over here, and I draw, and you should do this too, draw two separate pictures so you can see it, one for the normal force of the wall and one for the normal, or one for the mg. Again, the reason why we're just writing torque equations for normal force and mg is because since we put our axis of rotation at this point, that allows the lever arm for both friction and normal from the floor to be zero. So we can ignore these forces in terms of torque. These won't cause any torque, or the only things left, since these aren't at the axis of rotation, are these two forces. So these are the only two forces at the axis of rotation is there. That's going to cause the force. So that's how we know what two equations we need to write torque for. Okay, now rewind that and listen to what I just said, because I don't want to make this video too long by repeating and repeating what I'm saying, but we ignore forces, ignore torque where we put the axis of rotation. So for normal force of the wall, right, I draw the force, right, and then I draw my line of action. Again, the rules, I put them on several videos, so they're not up here. Obviously, there's no room. So the next thing is to draw your line of action through your force, and then you draw your lever arm, right, making a 90-degree angle with the line of action to the axis of rotation, making sure it's the shortest distance, right? And then in this case, that's what it is. So our R is the full length of the ladder, and the lever arm is right here, and this is the angle, right? So we're looking for this angle. That's what the question told us, but we know that in terms of the way squares and triangles work, this angle and this angle are the same, so I can write that over there, so I can associate the angle that I'm trying to look for with that force. All right, and then so when I write the equation again, just like everything else, you put your thing at that, we got to find out sign for torque, so you put your pencil or whatever, hold at the axis of rotation, apply the force. In this case, the normal is going to make this spin in a clockwise fashion, so it gets a negative sign, and then we write the force in there, right? The next thing is the force, which is the normal force from the wall, and the next thing is the lever arm, and the lever arm is that Rn, and then it's cosine, it's adjacent, the lever arm's adjacent to that angle, so cosine theta. So we put it right in there, all right? Now for the next question, we have, or not the next question, for the next torque, I'm sorry, for mg, we look at this force right here. So again, we draw our line of action here, and we know that this angle is going to be the same as this angle right here, okay? They're making the same, the mg is parallel to the wall, so that angle that the ladder is making with the wall is going to be the same as the angle that it's making with mg. Okay, so we know that these angles are the same, right? And then I want to draw my lever arm starting at 90 degrees from my line of action, which would be right here, right? That's 90 degrees, which is where we drew it, right? That's our lever arm right there, and that's the lever arm for mg, making sure that it goes to the axis of rotation. So when we need to write our torque equation, we know the force is mg. Oh, we got to get the sign for torque. That's my fault. So again, axis of rotation. This time, mg, right, if we hold at the at the axis of rotation and apply the mg, we see that this ladder would spin counterclockwise. So it gets a positive sign, so we just don't write a sign, just assume a positive. And then the force, right, which is mg, and then the lever arm, which is r, right, this r, which is half the distance. Remember, r is half the distance. We put mg in the center of the ladder, so r is going to be half the distance. So if the full length of the ladder is 8 meters, right, then that's going to be the r for the normal of the wall, where the r for the mg is going to be half of that because it's only half the length of the ladder. Okay, so it's going to be r mg, what we're calling it right now, but you'll see we'll kind of do something different. And then the lever arm is opposite of the angle here, right? This is the lever arm, this is the angle, so sine theta. Okay, so we have now two equations that have the angle that we're looking for in them. So let's go ahead and put them together in terms of Newton's first law for torque. So we write mg r sine theta minus the normal force of the wall r cosine theta, right? So this is coming from here. I just start with that one because it's positive. This one has a negative sign, so minus nw r cosine theta, okay? Right there, equals 0. Now remember, we're looking for theta, so we see theta here in two places. We want to solve this equation for theta. We're like, okay, cool, if I can solve this for theta, I'm probably done, right? Maybe, maybe not. So I bring normal force of the wall over because I want to get cosine and sine together, and I also know that sine over cosine is equal to tangent. Don't forget that. I think you all are pretty comfortable with that, but that's equal to tangent theta. So that's going to get you 1 theta. It'll turn these two separate thetas that I have into 1 theta, right? So I want to solve this equation in terms where I keep sine theta on top and cosine theta comes on the bottom. So when I do that, when I bring cosine theta over, right, I'm going to bring mg over here. Sorry, I said that so weird. So when cosine comes under sine theta, mg is going to come over normal force of the wall. I'm sorry I said that weird. That's what I was trying to say. And that's what we can see right here. So normal force and the r's. Remember, the r's are associated with the force. It's just the sine and cosine we're trying to get on one side. So the mgr, right, is what comes under the normal force of the wall in r, and just the cosine theta comes under the sine theta, as you can see there. So this becomes tangent theta, right, and this all stays the same. Normal force of the wall and the r of the, again, that's rn, if you're not too sure. That's rn, that's rmg. If you're wanting to know what these values are, but I'm not gonna write them, because you know what the r is by the force it's sitting next to, just so that you know, okay? So now we have tangent theta, and we want to solve for theta, so then we bring tangent, inverse of tangent over for theta, and we get this equation where we see it's the normal force of the wall times the r of the normal force, right? So the normal force of the wall times this, right, over, divided by mg, right, of the ladder, and the distance and the r of the ladder, the rmg, right? We see that, and we say, okay, well, we know mass, so we know mg, but we don't know normal force of the wall, right? And that's where the Newton laws come in. So you say, okay, well, the normal force of the wall is kind of like associated with friction here, and I know friction is equal to the mu, so I have the mu, so maybe there's something I can do there. So again, you're just trying to connect things, and you know how some things connect. We build you up to this idea. You know how friction and normal force are connected. You knew this already, right? So if you're saying, well, how did you know to make that step, Carl? We know that normal force and friction are connected. Maybe we can connect friction and the normal force of the wall together because we know they sit in the same plane. So maybe I can do something. That's how you get there. All right, so we do sum of forces in the x and sum of forces in the y. This thing isn't moving, so they're both in equilibrium. The sum of forces in the x are normal force of the wall, which is in the positive x direction, and friction, which is negative, right, is equal to 0. The sum of forces in the y are the normal force from the floor, and the mg, right, mg is negative, normal force of the floor is up, right, so normal force minus mg is equal to 0. And then we look at these equations and we say, okay, I need a normal force of the wall. Well, it's right here. So we'll solve this equation for normal force of the wall, right? I kind of skipped a step because I turned friction into mu times the normal force there, right? Before I brought friction over. So maybe that's the smart thing to do. You're like, normal force is there. I don't directly know friction, but I know mu, and I know friction is equal to mu times the normal force, so I'd want to swap that out real quick, right? Where it's mu times the normal force of the floor. Keep that in mind, not of the wall, the floor, right? The normal force of the floor. It's very, very important. So then I solve this equation, normal force of the wall minus mu times the normal force of the floor for the normal force of the wall, because that's what I'm looking for, right? I need that thing. And I say, well, now normal force of the wall is equal to mu times normal force of the floor. And you go, well, what the heck's the normal force of the floor? Well, over here in your sum of forces in the y, you see that. You say, oh, normal force of the floor is right there, and I know if this is equal to 0, I just have to bring mg over, and I can see that normal force of the floor is equal to mg. Right? You see that? So I can now look at the normal force of the wall equation that I have here and say, hey, I can sub that in there, which is what I do. So the final equation for the normal force of the wall is mu times mg, which are right, we have these values. We know the mass, we know mu, and g is 9.8. So we get happy. We say, cool, I can substitute normal force of the wall, this equation, mu times mg, into the normal force of the wall, for the normal force of the wall in this equation I have for the angle, and I should be able to solve it, and that's correct. So that's what we do here, right? It's mu times mg, and it's going to be over mg, and again, that's the distance, right? Don't forget that this r stays, okay? This r is that distance. It's a number. It's right here, and this is RMG, they're numbers. So don't let them drop off. So we write mu mg times Rn, and mg times, r of the normal force, and then that's above mg times r of the weight. Okay? Mg cancels out, right? Because mg, right? And we get a new equation where it's mu times the r for the normal of the wall, right, which is this, over r of mg, which is this right here. Again, these two numbers, right here, times the inverse, right, times the inverse of tangent, and we're done. That's our final answer. We have all these numbers. We have mu, we have these two r's, tangent you just put in your calculator, and you hit enter, and you'll get that theta. All right, so I know that was a lot. Walk through there. Go through the steps, okay? See how it was solved, and we're going to kind of do the same thing here. So maybe that'll help. It's just this problem is solved a little bit differently, but it's using somewhat the same steps. All right. So, and not to make these videos long, I'm going to end this video here, but I'm going to start this video, so you're going to see this still here. I want you to compare these two problems, actually all three. Okay. So once you've watched all three videos, I want you to go back and compare them and see, well, why did we solve this problem this way versus why did we solve this problem this way versus why we solved this problem this way. So again, don't stop. This is to be continued. We're going to do this one on the next video. I just don't want this video to be an hour long. Thanks for coming, and I'll see you on the next one.